What's up guys, and welcome to this video on question 5 of the 2017 final exam. Basically we're going to be going over work, energy and power. Okay, that's the focus of this question. Okay, so let's get straight into the question. 5.1. A box of mass 2 kilograms has an initial velocity vi. The box travels across a rough surface. Just going to put in there that that's a rough. And has a speed of 1.5 meters per second after it has traveled 0.7 meters. The frictional force acting on the box is 26 newtons. So I'm going to put there force friction equals 26 newtons. Okay, cool stuff. So question 5.1.1 is a definition. It says define frictional force. So the frictional force is the force that opposes the motion of an object. Okay, and we get ourselves 2 marks for that definition. Cool stuff. So question 5.1.2 says calculate the kinetic energy of the box. So we're looking for EK of the box while it is traveling at a velocity of 1.5 meters per second. So EK, the formula, is equal to, for our kinetic energy, is equal to 1/2 times the mass times the velocity squared. Okay, so we're looking at the mass of 2 kilograms, and we've been given a velocity of 1.5 meters per second squared. Okay, and if we put that into our calculator, we get a value of 2.25 and units of joules. Okay, and we get ourselves 3 marks for that. Cool stuff. So let's move on to question 5.1.3. Okay, so it says calculate the work. So calculate the work done on the box by the frictional force. Okay, so from our definition of work, we know that work is equal to a force times the change in distance or change in displacement, or we can say force times S. Okay, so work is equal to, the frictional force is 26 newtons. Okay, and the distance that it covers, or the change in displacement, S, is equal to 0.7. So times 0.7 meters, and if we put that into our calculator, we get that the work is equal to 18.2, and again this is work, so it's got units of joules. Okay, so that is our final answer. Okay, so question 5.1.4. Okay, I'm just going to do it next to it. 5.1.4. Okay, so state the work energy theorem. Okay, so this is a theorem that comes up all the time. Okay, so the definition of the work energy theorem is the work done by a net force on an object is equal to the change in kinetic energy of the object. So from this definition, we get the equation that work net is equal to F net change in S, which is equals to change in EK, or change in kinetic energy. Okay, so we get 2 marks for that as well. And then it says calculate the initial speed Vi or V1 of the box. Okay, so because we just spoke about the work energy theorem, I'm going to use that theorem. So 5.1.5, I'm going to use that the network work net is equal to the change in EK. Okay, so now we just need to think about this system. So if we draw a little free body diagram of what's happening here, let's take the positive direction as being to the right, because that's the direction that the box is moving. Our net force, or our force, is going to be the force friction, is the only force acting. We've obviously got weight, and we've got a normal force. Okay, so if we look at the forces acting in the horizontal plane, we just have the force friction. Okay, so, and the force friction is going to be in the negative direction because of our sign convention. So the work net is also going to be a negative, therefore, because it's acting against the motion. So we have minus 18.2, which is what we calculated before, is equal to our change in kinetic energy. Okay, so the kinetic energy initial was Okay, we can just say half mass times velocity final squared minus velocity initial squared. Okay, so we have minus 18,2 is equal to a half times the mass of 2 kilograms times the velocity final, which we know was given in the question as 1.5 meters per second, so 1.5 squared minus velocity 1 squared. Okay, so let's just change this to velocity 2 and velocity 1. So this would be position 2, v2, and this is v1. Okay, if we look at this equation, we have only one unknown, v1. So we can solve for v1, and that gives us a value of 4.52 meters per second. Okay, and v1, okay, it would have a direction, and the direction would be right. Because we have, if we calculate the maths, we actually get a positive answer out, which tells us it was moving to the right, and that obviously makes sense in relation to the question that we've just done. Okay, cool stuff, and we get 4 marks for that. Okay, so question 5.2. Okay, so let's get into it. A 1.2 kilogram crate is attached to a long string as shown in the diagram. A block of mass 0.4 kilograms collides with a stationary crate. Okay, so V of the crate here is 0 because we've been given that it's stationary, with a velocity VB, which is shown, and rebounds with a velocity of 0.36. Okay, so rebound tells us something that is going in the opposite direction after the collision. After the collision, it's going in the opposite direction. So this would be essentially a minus 0.36, causing the crate to swing through a vertical height of 65 centimeters or 0.65 meters. Okay, so what's happening is, essentially, if we had to draw this out, this block collides with the crate. Then after that, the block moves to the left and the crate swings upwards. Okay, cool stuff. Taking that into consideration, let's go into question 5.2.1, which is again a definition. Okay, so it says, state the principle of conservation of mechanical energy. Okay, so basically, in the absence of air resistance or any external forces, the mechanical energy of an object is constant. Okay, that would be the definition, and we get 2 marks for that. Okay, important to note, we had 6 marks in this question just from definitions. Okay, and basically from this definition, we get that the EK initial plus the EP initial is equal to the EK final plus the EP final for this system. Okay, now, and with that, we can go into the next question, which is 5.2.2. So calculate the magnitude. So we want the magnitude of the velocity of the crate immediately after the block collides with the crate. So basically, what we want to know is we want to use the conservation of mechanical energy to calculate the magnitude of the velocity. Okay, so what I'm going to do is I'm going to use the crate, this position as being position 1, and this position as being position 2. Okay, so we can say that EK1 plus EP1 is equal to EK2 plus EP2. Okay, and then what I'm also going to say is that at this point, or let's take the ground rather, from this point right here is our datum or our reference point. Okay, so at the bottom, we know that there is going to be a kinetic energy, so we're going to have half mass times velocity squared, but because it's at the datum, the EP goes to 0. Okay, and at the top, the maximum height that it reaches is 65 centimeters above. So at this position, V2 is equal to 0. So EK2 is also equal to 0. So we have that equals to mgh. Okay, so we have a half times 2 times the velocity, which is what we're looking for squared, is equal to the mass, which is 2 times 9,8, which is the gravitational constants, times the height that it gets to, which is 0.65 meters. Don't forget to convert this the centimeters to meters. Okay, and if we look at this equation, the only unknown is the velocity, so we can solve for v, and if we plug that in, we get 3.57 meters per second, and we've been told to find the magnitude, so we don't care about the direction, so that is our final solution. Okay, and we get 4 marks for that. Then 5.2.3, another definition, and so we actually get not 6 but 8 marks from definitions. Okay, so state the law of conservation of linear momentum. Okay, and the definition goes like, the total linear momentum of an isolated system remains constant. Okay, so basically from this we get that the momentum before, we can say the total momentum before a collision is equal to the total momentum after a collision. Okay, and the reason why I am saying total is because we have to take into consideration the momentum of both the block and the crate, or the collision there. Okay, let's clean that up again. Okay, so let's get into that question. Okay, so basically what we have to be concerned with is the block. So I'm going to say the momentum, remember, is equal to mass times velocity. So I'm going to say the mass of the block times the velocity of the block, everything on the left hand side is before, plus the mass of the crate times the velocity of the crate, all of this is in the before, is equal to the mass of the block times the velocity of the block, plus the mass of the crate times the velocity of the crate. All of that is after. Okay, so now we can start filling stuff in. So we know the mass of the block is 0.4. Okay, and obviously what we're looking to do is calculate the magnitude of the velocity of the block. So we're looking for this right here, velocity of the block just before it collides with the crate. Okay, so what we're looking for is that value right there. So that's going to be our unknown. Okay, we know that the velocity of the crate initially was 0, so it was a stationary in the question, so that term goes to 0. So this is equal to the mass of the block, which is 0.4, times the velocity of the block after the collision, which we discussed is minus 0.36 because it rebounds. Okay, so minus 0.36 plus the mass of the crate, which was 1.2 kilograms, times the velocity of the crate, which we calculated before, which was 3.57 meters per second. Okay, if we look at this equation, we have only one unknown, which is the velocity of the block before the collision, and so we can calculate VB is equal to 10.35 meters per second. And again, we only care about the magnitude. If we didn't and we wanted a direction, this would be to the right. Okay, but just that I've underlined is sufficient for this question. Okay, guys, so we get 4 marks for that and a total of 26 marks, which is a lot of marks. And yeah, so like I said, 8 of those marks come from definitions. So if you know your definitions well, then it will definitely help you with the exam. Okay, thanks for watching, guys, and in the next video we will do question 6.